reference. And then make one of I'll just acknowledge it. That's your paper for what? Yes. Yeah.
All right, so I'm told it's time to go. Yeah. No, I'm saying no, it's not time to go.
Not till the boss introduces you. Right?
Oh, I'm getting that. I don't know what that is. That looks like go, but maybe it's not. I don't know.
That's what I said. No.
Wait.
Ah, yeah, okay.
I introduce you.
I don't know what this means. I gotta interpret that as go.
No, it's just let's see before a couple of minutes to arrive. How are you doing? Absolutely. All right. All right, so before introducing our speaker, let me remind you of the events in the coming days. On Friday, Tushar Menon, who is a center visiting fellow, will be talking about scientific realism as a normative notion twice over. On Tuesday, Karl Hofer, who is our senior visiting fellow this year, will be talking about generic causation in complex mind-dependent systems. Looking forward to this talk. On Friday next week, we have the second lectures in the annual lecture series given by Colin Klein at 3:30 on the 10th floor. And the topic will be transformers, representational structures, and the language of thought. We're all invited to these talks on Tuesday next week. This week and next week, and on Friday at 3:30. There, it's my great pleasure to introduce Eric Snyder, who is Associate Professor of Philosophy at Ashoka University in India. Eric is also a visiting fellow at the center this semester. We're extremely lucky to have him with us for a whole semester. He works in the philosophy of language, the philosophy of metaphysics, of mathematics, semantics, as well as the philosophy of mind and cognitive science. He has published widely on all of these topics in journals such as Synthèse, Erkenntnis, Nous, Linguistics and Philosophy, Inquiry, and other languages. So he has published quite a lot. He has already published 2 books. And I've got the title somewhere. Okay. The first one is Semantics and the Ontology of Number in 2021 with Cambridge. And the second one with Richard Samuels, who is also visiting us today, Number Concepts, an Interdisciplinary Inquiry. He is working on 2 more books, busy man. The first one is The Nature and Content of Number Concept with Richard Samuel and Stu Shapiro. From OSU, and the other book is Plurality and Paradox in Natural Language. You have a sense of when those books are going to be written?
Richard?
Soon is the answer.
Yeah.
All right. All right, looking forward to these 2 books. And today, Eric will be talking about his knowledge of Successor due to knowledge of Morphosyntax. Floor is yours.
Thank you. So first, thanks for coming. Yeah, so this is part of a bigger project, as Edward was suggesting. Part of this big book project that Richard Samuels and Stuart Shapiro and I are engaged in. You might think of it as sort of the descriptive metaphysics of number. So what do our number words mean? What are our number concepts? How do those 2 things interact? And what can that tell us about traditional issues within the philosophy of mathematics? Today, I'm going to be talking about more of the second issue, concepts, number concepts, and specifically what are best extant psychological theories to tell us about how kids acquire number concepts, and maybe also what those concepts are like. I'm going to be largely critical for the most part, but one of the upshots is going to be that I'm going to suggest a new empirical hypothesis, one that, as far as I know, has not been even considered within developmental psychology. And hopefully I'll explain why it's clear, make it clear why no developmentalists have really even considered this possibility. This is joint work with Richard. So, but all problems are mine. So any obvious incoherencies or whatever, you can blame that on me. Okay, let's do it. So some empirical background. So over the past few decades, a number of cognition researchers, so developmental psychologists, cognitive scientists, have paid extensive attention to how children acquire tacit knowledge of successor. I'm going to be talking a lot about knowledge here. I always mean tacit knowledge. I don't mean the kind of justificatory kind of thing that we're used to in epistemology. Okay. So there are multiple motivations. One of them is just a general developmental concern about grasping the concept of successor. That seems like an important, interesting milestone in its own right. The second has to do with what number concepts are like. So Susan Carey, for example, says that successor is somehow constitutive of grasping the concept natural number. A third motivation is, and maybe the most obvious, is productivity. How is it that kids can produce concepts, number concepts of larger and larger sizes, right? So 20, 21, 103, 10,400, etc. How do they acquire these concepts? Why are they productive? Why can they generate more and more of these concepts? Natural idea is they understand something like successor. Okay. So in seeking to explain knowledge of successor, many researchers have proposed that knowledge of natural language morphosyntax is essential. The kid has to have knowledge of the morphosyntactic principles that generate specifically, oh wait, I'm going to get to that, what I'm going to call count words. Words that are used for counting, answering how many questions. But ultimately, this leads to what I call the knowledge thesis. Knowledge of natural language morphosyntax explains knowledge of successor. So that's the central thesis I'm considering. And here's the very basic idea behind the thesis. Of the known cognitive resources, we want to explain how kids acquire a concept of successor. Natural language morphosyntax seems like an especially plausible candidate. Why is that? Well, that's because natural language morphosyntax is recursive in the same way that the successor function is recursive, right? So if you want to explain how a kid acquires successor, appeal to something that already has that sort of property and that they already have tacit knowledge of. So it's a very natural idea. So I'm going to focus on two versions of the knowledge thesis today. These are the two primary versions of the knowledge thesis. As far as I know, they might be the only versions of the knowledge thesis. The first is what I'm going to call the merge model. So knowledge of successor is due to a very general, perhaps the most general syntactic principle, at least within mainstream transformational syntax, that's called merge. I'll talk about that later. The second one is called the complex, I'm calling it the complex cardinal model. So knowledge of successor is due to knowledge of morphosyntactic principles, specifically responsible for generating count words. Again, by count word, I mean just number words that are used to answer how many questions and that are used to count. Okay. Again, 1, 12, 22, 103, etc. All of those are count words as I understand them. So I'm going to argue for three claims. First, merge models face a variation of the very famous identification problem due to Benacerraf. And so, at least from my vantage, they're probably non-starters. Secondly, current formulations of the complex cardinal model face serious empirical difficulties. So first of all, they implausibly require that numbers are cardinalities. So by cardinalities, I mean the sorts of things that represent how many quote-unquote constituents belong to a quote-unquote collection. The quotes there are due to the fact that different philosophers hold different views about what collections are, and we don't care. pick your favorite view of what a collection is. It could be a set, it could be a sum, it could be a plurally referenced individual, and likewise for a corresponding notion of constituent. Okay. Secondly, they implausibly require that natural language count words are actually infinite as opposed to merely potentially infinite. I'll discuss that distinction later. And here's the, well, that's negative. Here's the positive bit. Despite these problems, the complex cardinal model should not be rejected out of hand. Rather, there's a way of productively reformulating the model, which results in a novel and I think plausible hypothesis regarding the nature of children's number concepts. They are what we're going to call folk Aristotelians. Okay. So that was the introduction. I'll next focus on some very brief reminders about what successor is. You're not going to need most of that, I suspect. Then I'll focus on the merge models, talk about the identification problem, move to complex cardinal models, discuss those two problems I just mentioned. And then I'll give you three conclusions for the upshot of this discussion. Okay, so here are some reminders about successor and sort of what the implications of that are to keep in mind. So the notion of successor studied by psychologists is the one that's codified in the data-piano axioms. Those are the axioms of basic arithmetic. So minimally, these provide an axiom specifying an initial element, 0 or 1, depending on who you ask. Axioms specify a function, namely the successor function, which maps every natural number to a unique next natural number. Nothing new there. So here's a very a typical informal characterization of those axioms, forgetting about induction, because that's not going to matter to us. So 1 is a natural number, 1 is not the successor of any natural number. Each natural number has a successor, and successor is 1, 1. So it's a function. And proponents of the knowledge thesis, I'm going to be talking mostly about psychologists and cognitive scientists, but there are also plenty of philosophers who hold this sort of view as well. So, they're concerned with this specific notion of successor as defined by the data-piano axioms. So here's a quote from David Barner's group. I'm going to be mentioning them a lot in this talk because they have done the most recent research on successor, infinity, and related issues. So they say by around 6 years of age, many children appear to understand that numbers are infinite, and that for any number n, any number has a successor whose value is n plus 1, in keeping with an intuitive understanding of the piano axiom. So it's clear that they are referring to those specific axioms in relation to what they mean by successor. And likewise for everyone in this solution, right? This is just a widely accepted view. Okay. So call the relation defined by the data-piano axioms numerical successor. Why am I giving this a special label, special name? Because it turns out there are all sorts of successor-like relations that psychologists and cognitive scientists use, which aren't numerical successor. So for example, there's a relation of what we might call count word successor. So for any pair of count words in a count list, that is to say, a list of count words canonically ordered 1, 2, 3, 4, etc. So for any pair of those, the second is the immediate successor of the first. That's a relation on words, right? Not numbers. Here's a second one. If you know a little bit about Frege, this was Frege's notion of successor, although it's put in set theoretic terms. So a relation holding between two collections of sets such that for any set in the first, if there's not an object, if there's an object that's not in that first, adding that object to the first makes the first collection of, sorry, the first set in 1-1 corresponds with the second. So you have two sets, and intuitively one has one less member than the other, and adding a new member to that first makes it have the same cardinality as the second. That's the basic idea. We call that cardinal successor. Notice that, sorry, I'll get to this point in a second, but notice that these are not the successor relation as defined by the data-piano axioms, unless you just think that numbers are words, count words, or you just think that natural numbers are collections of sets, right? Collections of equal numerous sets, as Frege, for example, held, and also Russell. Okay, so sometimes those two principles I just mentioned are combined into a single principle. So Susan Carey confusingly calls the following principle the successor function. For any count word n, we're talking about words, the next count word s of n, that's count word successor, in the count sequence refers to the cardinality, now we're talking about cardinal successor, n plus 1, attained by adding one element to collectors whose cardinality is denoted by n. So that just combines what I call count word successor with cardinal successor into one sort of principle. And she calls that the successor function. Make it sound like it's the function that's defined by the Dedekind-Peano axioms. Maybe it is, but you need some auxiliary assumptions in order to make that work out. Right? I'll spell out what those assumptions are later. And again, obviously, that doesn't specify the notion of successor as defined by the Dedekind-Peano axioms, and thus the very target that psychologists are interested in, unless you assume that numbers just are number words or that they are collections of equivalent strings. Maybe both. Okay. The second property of the natural numbers as specified by the Dedekind-Peano axioms is that they form what's called an omega sequence. That's an infinite discretely ordered series with an initial element, again, typically 0 or 1. Psychologists seeking to explain knowledge of successor typically want to explain the following principle, acquisition of the following principle that follows in virtue of the axioms. Call it the successor principle. Every natural number has a unique successor. That's the target. They want to explain knowledge of that, ultimately. Again, tacit knowledge of that. So relatedly, psychologists are often concerned to explain how children come to know that there is, quote unquote, no highest number. So something in the neighborhood of infinity. So here's another quote from Barner et al. A child who truly understands the successor function should not only know that the successor of 5 is 6, or that the successor of 16 is 17, but also that for any number n, this number has a unique successor whose value is n plus 1, and thus there is, quote unquote, no highest number. Very intuitive way of cashing out what knowledge of successor might be like. But there are two senses in which there may be no highest number. The first is the familiar one, all this actualism about the natural numbers. For every natural number, there is a next natural number, right? So the natural numbers form an actual infinity, a completed totality, if you like, such that it has a greater cardinality than any finite collection. So that's one way in which there may be no highest number, because they're actually infinite. There's a second, more historically relevant notion here, which is potential infinite. The one that Aristotle held, it's the one that Leibniz held, it's the one that Gauss held, or basically some of the greatest minds in history prior to Cantor, this was the predominant notion of successor that we have. The natural numbers are potentially infinite. For any natural number, there could be a next natural number. So again, in that sense, of course, there is no highest number. Why? Well, pick the supposed highest one. Well, there could be a next one, right? So it's not the highest after all. Okay, so clearly the Dedekind-Peano axioms entail an actualist notion of successor, right? They codify an actualist. So again, insofar as we're trying to explain knowledge of that notion of successor, our account had better be actualist, not potentialist. Okay, so merge models and the identification problem. So according to the merge model, knowledge of natural numbers is due to a very general syntactic principle known as merge. This is a principle of the minimalist program. So basically what it does is it takes any two lexical items and forms a set of those two lexical items. So here's the basic idea. Recursive application of merge to a single lexical item generates a sequence of sets, which can then serve as a model of basic arithmetic, similar to other set theoretic models, which I'll mention here in a minute. Thus, recursively applying merge, to quote Chomsky, yields the successor function. And it is straightforward to define addition in terms of applying merge to lexical items, and in familiar ways, the rest of arithmetic. So recursively applying merge not only explains knowledge of successor, why? Because we have knowledge of merge by hypothesis, generates the very objects that are the objects of arithmetic, numbers and relations on numbers. Numbers just are sets that are generated by merge, according to Chomsky. So since, as I said, merge generates sets of lexical items, it generates numbers and those relations on numbers, just in case the sets that are generated are numbers. We have to make this ontological assumption in order for this to make any sense. Okay, so there's going to be two versions of the merge model I talked about. There's Chomsky's version, and then there's an updated version of that. Here's Chomsky's version. So begin with any lexical item. Say the English word one. Identify it with the number one. Now apply merge to 1 and 1. That gives you the set containing 1. Identify that with 2. And now apply this definition of successor. And what you end up generating is sets that look like this. Right? So 3 is the set containing 1 and 1, so on and so forth. What you get is a set theoretic model of the natural numbers. You generate an omega sequence. Right? So that's one version. There's a second version due to Watanabe, another syntactician, whose view is very similar to Chomsky's with two additions. First, shift the sequence over by 1. So rather than starting with a single lexical item, say 1, and identifying it with the number 1, shift the sequence over 1 so that you can identify 1 with the set containing whatever that is. The second change here is that rather than using any specific lexical item, say the word 1 or the word cat or whatever, pick your favorite lexical item, we're now going to employ a variable over lexical items. So this is I. I ranges over lexical items, maybe of a specific language, maybe over all languages. And then we're going to generate numbers in the same way that we did for Chomsky. So we identify 1 with the set containing I. We have this definition of successor, and we just keep applying it to the sets that are generated. And again, what we get is a set theoretic model of the natural numbers. We generate an omega sequence. This makes sense? Now, we have these two versions. Which should we prefer and why? Watanabe gives us two reasons for preferring his version. And here they are. So since Chomsky identifies the number 1 with a particular lexical item, he can't incorporate the number 0. Remember, some definitions of the natural numbers include 0-sum. So one apparent advantage of Watanabe's version is he can incorporate 0, whereas Chomsky can't. How does he do that? Just identify 0 with the empty set. Apply the definition of successor, and then you generate the sets, just as he suggested. Okay, so that's one advantage. The second advantage is that Watanabe's version purports to explain what's called the cardinal principle. Roughly what this states is, if you count some f's by matching them 1-to-1 with some number words, canonically ordered, then the last number word you use in counting the f's designates the cardinality of the f's, the number of the f's. And Watanabe argues that his version of the merge model explains this. I won't go into details here, but let's just spot on that. Okay. The major challenge for either version is going to be the very famous identification problem due to Paul Benacerraf. I imagine many of you know what that is. Just in case you don't, since we can't choose between infinitely many set theoretic models of the natural numbers without complete arbitrariness, Benacerraf argues that numbers can't be sets at all. So here's the famous quote: if numbers are sets, then they must be particular sets. But if the number 3 is really one set rather than another, it must be possible to give some cogent reason for thinking so. But there seems to be little to choose among these two accounts. These are the familiar set theoretic models, von Neumann ordinals, and the Zermelo ordinals. Generally, if you take a class in set theory, you model the natural numbers using one of these two sequences of sets. And these are the sets that Benacerraf has in mind. So there seems to be little to choose among those two accounts. Why? Because they're both perfectly good models of arithmetic. Right? So if all the above is kosher, oh, and by the way, there are infinitely many of those. Why? Because any omega sequence is a model of arithmetic. There are infinitely many omega sequences. There are infinitely many seemingly equally good models of arithmetic. So if all the above is cogent, then any feature of an account that identifies 3 with a set is a superfluous one, and therefore the number 3 and its fellow numbers cannot be sets at all. Okay, so that's the famous argument against numbers being sets. Obviously, merge models identify numbers with sets. And Watanabe is aware of the challenge. I don't know if Chomsky addresses it, but at least Watanabe does. And here's the response. His models to be preferred over other set theoretic models. Remember, there are infinitely many of them. In fact, there are infinitely many of his own model, but he doesn't seem to recognize that. Because it captures the relationship between natural language and natural number. Specifically, Watanabe's choice of sets is not arbitrary, he seems to suggest. Since we ought to prefer a set theoretic model that captures this relationship between natural language, meanings of number words, and natural numbers themselves, the denotations, presumed denotations of numbers. So there are 3 maybe obvious problems with this response. First, it just presupposes, without any kind of argument, a very highly contentious program within linguistics, minimalism. Minimalism is not the only game in town, even in terms of syntax. There are variations of minimalism, why this specific one, etc. There's no evident reason why an account of what numbers are should explain the relationship between them and natural language, right? This is a metaphysical question. What are natural numbers? Why shouldn't an account of what the numbers are have to be such that it explains what the relationship between them and the natural language is, right? Number words. So by comparison, we don't expect an account of what water is, right? A metaphysical theory of what water is to explain its relationship to natural language, right? So why should things be any different with respect to number? Again, Watanabe just doesn't address this. The main problem here is that we just generate a new version of the identity problem. So it's a dilemma. Remember, it uses this variable I over lexical items. Intuitively, variables aren't lexical items. They're variables over lexical items, right? So the variable I is not part of English or any other natural language. That's immediately problematic. Why? Because merge applies to lexical items. So it doesn't apply to this variable, and therefore does not generate the sets that Watanabe thinks it generates. But suppose it was a lexical item. And so it did generate the sets in the way that Watanabe says. Well, in any formal language, you take first order logic, someone will tell you that there are infinitely many variables. Likewise in any formal system. Okay, so since we're assuming that I is a lexical item and we have infinitely many variables, now we have to pick. Why that one as opposed to the other infinitely many variables? Right? It seems completely arbitrary. So we just generate the identity problem, the identification problem all over it. This makes sense? Seems like a non-starter. Can we do better? Yeah, maybe. So there are these other models, complex cardinal models. Okay, so according to these, knowledge of successor is due to knowledge of count word morphosyntax. Remember, specifically, those are morphosyntactic principles that generate count words, not all of the grammar, as with merge, for example. So here's the basic idea that's summarized quite nicely. Exposure to counting might lead to children to move beyond a memorized list, that is, count words, to derive productive rules that allow them to count indefinitely high, and that these rules might be the basis for deriving a recursive successor function. Knowledge that counting words are governed by a rule-like structure might lead them to infer that numbers themselves are generated by a recursive successor function, right? Very intuitive idea. So that's explicit in Barner et al.'s work, but it's also very plausibly implicit in many theories, psychological theories. Susan Carey, I think, is pretty explicitly married to this view. Dave Barner, in his own solo work, says something like this. Liz Spelke is similarly has a view like this. So it's a very widespread sort of view. The basic idea is that children somehow infer knowledge of successor based on their tacit knowledge of morphosyntax, count word morphosyntax. So again, through learning such productive rules, that is the rules governing generation of count words, children may infer that every number has a successor, and by extension, that numbers are themselves unbounded. Again, there is no highest number. So the suggestion seems to be that there are two sort of sub-inferences that are involved. So we start with tacit knowledge of some morphosyntactic principles. These are the ones that generate count words. I'll give you an idea of what they may look like here in a second. From that, the kid infers that every count word is followed by a unique next count word. And from that, they infer that every number is followed by a unique next number. So there's sort of two inferences going on. So it's easy to understand why this might be a key one. So again, if we want to explain how kids have knowledge of successor, this seems like an especially plausible candidate. Why? Because morphosyntax is recursive, right? Like all syntactic principles. That's the basis for syntax. So there are recursive morphosyntactic principles which combine simplex number words. Those are words like 1, 2, 3. They're morphologically simple. They're not built out of more complex things. In English, they probably go through 12. With morphemes like teen, 13, 14, etc., T, 20, 22, 23, and lexical powers like 100,000 million. We combine these together syntactically to form more complex number words, like, for example, 2,348. If you want to know how this works, there's a book on this by Herford. It doesn't really work, but it gives you an idea of sort of what those principles might look like. So in Herford's grammar, for example, you can generate this string without and. He doesn't include and for some reason, but maybe you could throw it in. And it's recursive. So you can just generate these structures of indefinite length. So you can generate more and more complex number words. The details aren't really important. It's just the important point is that we can seemingly do this. So given a finite stock of simplex number words, morphemes, lexical powers, the grammar generates number words without limit, at least in principle. There's also another side of this, which is the semantics of number words. We also know how this works. There's a book by Ian and Chomsky, which deals with semantics of complex number words. It links up very nicely to this kind of recursive grammar. So we've got a pretty good picture of how complex number words are not only generated syntactically, but also how we understand their meanings. So how is it that you understand that string? Well, two reasons. One, you have syntactic principles that generate the string. But secondly, you've got general semantic principles of interpretation, namely function application, really all you need here. And that will generate meanings for the whole based on meanings of parts. So compositionality, right? So we know how this works, more or less. Maybe not so much in the syntax, but at least we know how it works in the semantics. Okay, so how might children acquire knowledge of successor on that basis? Well, by understanding count word morphosyntax, they somehow infer next count word. So every count word is followed by a unique next count word. Right? They already know how to generate more and more count words. So that seems like a fair enough inference to draw on that basis. Psychologists don't know exactly what the nature of this inference is, and we don't either. Let's just spot that it happens. So step two, they come to believe next count, by coming to believe next count word, children subsequently infer what we call the successor principle. Every number is followed by a unique next number. Here's an important question. What do children think numbers are at this point? So all we're assuming at this point is that they have knowledge of morphosyntax. Well, they might think that numbers just are number words. That's a plausible enough sort of assumption to make. But it's pretty clear that psychologists don't think that. That's called formalism within the philosophy of mathematics. for the most part, psychologists don't seem to be formalists, even though they sometimes speak this way. Rather, most of them pretty explicitly assume that numbers are the denotations of count words, right? Specifically, numbers are cardinal numbers, right, in the set theoretic sense. Okay. Yeah, so again, it's pretty clear that they assume the second option. Roughly, the idea is going to be that if every count word picks out a cardinal number, then every count word, and if every count word is followed by a unique next count word, then every cardinal number will be followed by a unique next cardinal number, and that just is the successor function, assuming numbers are cardinal numbers. Right. Make sense? Unfortunately, psychologists never really spell this out in any detail, but we can do better. Richard and I have a small monograph on this if you want to know the details. And here's the basic idea. So assuming children have mastered morphosyntax and semantics of count words, they will have tacit knowledge of what we might call the semantic thesis. For any adjacent pair of count words in the count list, alpha and beta, the denotation of beta is the cardinal successor of the denotation of alpha. We're going to be assumed, well, by hypothesis, the child already tacitly believes what we call the next count word. Every count word is followed by a unique next one. Now all they need to assume is something about the nature of the denotations of count words, namely that they denote cardinal numbers. They assume all three of those together, because those jointly entail the successor principle, right? Every number is followed by a unique next number. You might see how knowledge of successor might arise, given these three assumptions. Note that this assumes that numbers are collections of equanimous sets. Sometimes, but not always, psychologists are pretty explicit about this. Susan Carey, for example, is. So what are, I just gave you a semi-formal account of how this might work. I've just assumed that we know what count words are and that we know what their denotations are, et cetera. Well, maybe we should back up just a second and ask, well, what exactly are count words anyway? The count words we said are number words used for counting and answering how many questions. But here's an important fact. Number words are used in lots of different ways. Got a small monograph on this too, if you want to know more about it. Here are three of them. Mars's moons are 2 in number. There 2 is being used as a predicate. Mars's 2 moons are red. There 2 is functioning as modifier. 2 is an even number. There 2 is a name. What philosophers call a singular term, functioning referentially. Why is this important? Predicates, modifiers, names, singular terms, I guess, have different semantic types, and therefore they have different denotations, at least within contemporary semantic theory. So specifically, in the predictive use, it's typically assumed that 2 denotes a set of what you might call collections of pluralities, right? Things that have exactly 2 constituents. And in the third case, where 2 is a numeral, it refers to a number. Why is that important? Well, this is the story I just told. The denotations of count words are numbers, right? But different uses of number words have different denotations. So it had better turn out that count words are numerals, right? If this story is going to work out. So it's important to figure out what count words are. That's why I'm asking this question. And one way of answering the question would be to look at the sorts of tests that psychologists use when probing for knowledge of count lists. Why? Because count lists contain count words, right, by definition. So here are the 2 most popular, or at least well-known, tests that psychologists use for probing knowledge of count lists. They're both due to Karen Wynn. To give in tasks, ask a kid to place hand over, say, 2 Elmos, and success is indicated by the kid handing over exactly 2 Elmos. Another one's called the how many task. Just ask the kid, hey, how many Elmos are there? And if they give you the right number, great, that's success, right? Kids start doing this pretty well, starting around age 2, and it's sort of this progression, slow progression up. And they master counting somewhere around 4.5, 5. maybe, depending on what you count as mastering counting. Okay. So based on those two diagnostics, it's pretty clear that number words are cardinal adjectives. I in here is a modifier, obviously. That's an adjective. Answering how many questions? Well, I'll give you evidence that these are cardinal adjectives in just a bit. Take my word for it. So here's the first objection. Numbers are reference of number words used referentially, right? Number words as singular terms. These are the denotations of numerals, not cardinal adjectives. But we just said count words are most plausibly cardinal adjectives. Here's a reply. What's the difference? After all, Frege and Russell told us what numbers are. They are collections of equinumerous sets. And you might think that the denotation of a cardinal adjective is exactly that, right? So the problem with that idea is that it violates compositionality. Compositionality requires that if two occurrences of an expression have the same denotation, then they also need to have the same semantic type. Singular terms modifiers, by definition, have different semantic types. So this is only going to work if you assume that semantics is not compositional, which for me is game over. Here's the second reply. There are referential uses of count words. Just consider the sorts of examples that Frege gave us. The number of Elmos on the table is 2. These are called specificational sentences. I've got a paper on it in case you're interested. And plausibly, 2 here occurs within that kind of sentence. And it is a cardinal adjective. Why? Because it can be modified and it can modify. So it is an adjective there. It very plausibly is a singular term. My favorite analysis of specificational sentences, it does function as a singular term. Intuitively, we can infer from that sentence that Mars's moons has a cardinality. That looks like existential generalization, which is only valid on singular terms. And also it answers a how many question, namely how many moons does Jupiter have? Namely 2. So by the way we define what a count word is, it's a count word, but it's also functioning referentially. Make sense? Okay. So this suggests a weakening of one of the theses that I mentioned earlier. Call it restricted count word denotations. The original one was count words denote cardinal numbers, remember. On this restricted version, it's only count words as they occur in those sorts of sentences. Referential uses of count words. Does this make sense? So maybe that'll save it. That'll save the proposed explanation. The problem is that numbers aren't cardinalities, the sorts of things that count words, if they were, when they would refer to. Why is that? Well, because there's lots of semantic evidence that suggests that numbers are not cardinalities. Again, I've got a small monograph on it. So here's the argument. If numbers were cardinalities, then we'd expect numerals and co-referential singular terms like the number 2 be acceptably substitutable for cardinality referring terms like the number of Mars's moons across a wide variety of syntactic contexts, and we just don't see that. So I'll give you some examples. The number of Mars's moons is 2, good. The number of Mars's moons is the natural number 2, bad. The number Mary is researching is 2, that's fine. The number Mary is researching is the natural number 2, that's also perfectly fine. How many moons does Mars have? 2. Good. How many moons does Mars have? The natural number 2. Awful. Which number is Mary researching? 2. Good. The number 2. Good. Why is there this contrast here? Mary found out the number of Mars's moons. Okay. Mary found out the number 2. Weird, right? The bridge collapsed due to the number 200. That's very strange. The number of candidates is expanding rapidly. That's fine. The number 2 is expanding rapidly. It's just weird. It presupposes that it's some sort of physical thing. That's the natural number 2. Good. That's the natural number of Mars's moons. Weird. And finally, that's the exact number of Mars's moons. Fine. That's the exact number of sorry, that's the exact number 2 mu. What does all this suggest? This, and by the way, these sorts of contrasts occur across natural language, not just English. What's this suggesting? It's suggesting that natural language draws a distinction between cardinalities, the sorts of things that answer how many questions or designate how many things belong to a collection, and numbers as such. At least that's the conclusion that I come to, and also Friederike Moltmann. Okay. So that's the first problem. The second problem is that count lists aren't actually infinite. Remember that according to next count word, every count word is followed by a unique next count word. That's an actualist notion, right? A count of infinity. But on any remotely plausible morphosyntax for count words, will be at most potentially infinite. Why? Because there is a finite stock of lexical powers in any natural language. Those are words like 100, 1,000, million, etc. So these sorts of words, the lexical powers, they are productive, so we can productively generate them, but only up to a point. So at some point, the morphosyntactic rules just get out, and we just sort of name numbers willy-nilly. So that's what happens with, say, Google or Googleplex, Skew's number, Ryo's number. Last time we gave this talk, Ryo was one of the participants, so that was kind of fun. Here's the point. These sorts of lexical power names for lexical powers are not generated by morphosyntax. We just stipulate. So there is a finite upper limit on the number of words that can be produced within any natural language. In fact, this was codified as a linguistic universal by Greenberg. But the same point is made by Grinstead et al. While the system is indeed potentially infinite, the ability to count to an infinitely high number is contingent upon an ability to invent new words for powers of 1,000. So we can always generate a next number word, just we have to make it up through the process of lexical invention. Yeah, we can do this. Of course we can. But the point is, morphosyntax itself won't do it. So emphasis here is on potential infinity. Notice that I highlighted, there is a potential infinity of count words. So we can always produce a next count word thanks to our ability to invent new words, but it didn't follow that there is a next count word generated by morphosyntax. Make sense? Okay. So here's a natural reply. I think we've actually heard this from Dave Barner a couple occasions. Look, children aren't perfect reasoners, right? We're not giving a logical deduction here. What we're trying to do is explain the beliefs that kids have, right? We're not trying to justify the beliefs they have. So, do you really think that children know that there's a finite stock of lexical powers in their language? No, of course not. Why would they know that? So then what would prevent them from making this inference based on their knowledge of morphosyntax, namely that natural numbers are infinite, right? It may seem like a perfectly good inference to them. We think a combination of factors suggests resisting this sort of reply. So first, in general, the following appears to be a widely respected methodological precept regarding model selection in cognitive science. You might want to press back on that, I don't know. We're calling it modest rationality. All else being equal, we should prefer cognitive models that avoid unnecessarily imputing error or irrationality to an agent. So just seems plausible. Take it on board. Combining that with the fact that there is no good empirical reason to impute this sort of error on behalf of children suggests that you shouldn't do it. In fact, we're going to argue that the empirical evidence suggests that you should not impute error in this way to children. Why? Because there are tons of recent studies on infinity which suggest the opposite conclusion. Most of these experiments are due to Dave Barner and his collaborators. The main probe that they use is what's called the infinity probe, which is just a series of 6 questions that they ask kids in an order. So 3 of these questions have to do specifically with successor, and here's what they are. If we thought of a really big number, could we always add to it and make it even bigger, or is there a number so big we couldn't add to it anymore? That's one question they ask. You said that the biggest number you know is x. Tell me, is it possible to add 1 to x? Or is x the biggest number possible? Could I keep adding 1? What would happen if I kept adding 1? They're asking 5-year-olds and 6-year-olds these sorts of questions. So that study builds on previous studies that were done in the 80s, known as the Infinity Interview, where again, they just basically ask kids questions like, can people always add to make a bigger number? Or is their number so big we couldn't add to it anymore? You'll notice all the underlying modals here. You can anticipate the point I'm going to be making. So 3 points about the research bear emphasizing. First, children's knowledge of numerical infinity comes well after they learn how to count. So this is occurring somewhere between 5 and 7, whereas they learn to master counting well before them. Secondly, all the questions that I just underlined have modals in them. Can you do this? Is it possible to do that? That sort of thing. And again, modality is the characteristic of potential infinity, not actual. Such knowledge is assumed to be knowledge of numerical successor. Successor as defined by the data-container axioms. So again, here's Barner and colleagues. At this stage, children appear to know that every number has a successor. This is coming from the same paper in which the Infinity Interview is given, right? And that numbers are infinite. That is knowledge of successor as specified by the data-container axioms. So what they're claiming is that at the age of 6, kids understand numerical successor, the successor relation as defined by the data-container axioms, and therefore they possess a conception of actual infinity. That's the claim. But clearly this conflates potential infinity with actual infinity, right? So given the nature of the probe questions, namely that they're all formulated in terms of modality, which is characteristic of potential infinity, at best it would suggest what we might call potentialist next number. Every number could be followed by a unique next natural number. That's what the evidence is suggesting here, right? It certainly doesn't give us any evidence for an actual infinity of natural numbers. I'm almost done. So 3 conclusions based on all this stuff. There's going to be people here who know this way better than I do. Aristotle held the following 2 views about natural numbers. I'm fairly certain of that. First, numbers are cardinalities. That is to say, a natural number is always a number of something. Basic distinction between number as a monadic predicate, number of as a relational predicate. Numbers are potentially infinite. For every number, there could be a next number. So those are 2 Aristotelian views. Call anyone whose intuitive conception of the natural numbers consists of those 2 views a folk Aristotelian. So assume some version of the complex cardinal model is right, broadly speaking. That would suggest a new hypothesis, a new empirical hypothesis, one that, as far as we're aware, no psychologist has ever considered. Call it the folk Aristotelian hypothesis. When first grasping successor, kids are folk Aristotelians. They think of numbers as cardinalities, and they think of numbers as potentially infinite. That's what all the infinity interviews would recommend, would suggest. And again, if we assume that these models are broadly correct, they're assuming that numbers are cardinalities. So insofar as those explanations are onto something, they suggest that kids are folk Aristotelians. So that's one empirical point to be drawn from all this. And now here are 2 methodological points, I take it. First, just as a point of general methodology, don't assume that the concepts that kids have are the ones that are defined within textbook mathematics. This happens all over the place, at least in this area of cognitive and psychology, but I suspect it may happen elsewhere. I don't know. So it's very common. If you want to know what a kid's concept of mathematical concept that X is, we'll go to a textbook and see how X is defined within that textbook. And this is completely understandable, right? If you want to know what a concept of X is, you need to know what X's are. Our best theory is our mathematical theory, so you might start there, right? But just in this case, right, the data-container axioms for the product of millennia of really hard-won work, namely mostly by Cantor, So as I said, most philosophers and mathematicians prior to Cantor were potentialists. Why should we assume that children side with Cantor on this particular debate, right? Why should we assume that? The second methodological point is that if all of this is right, there are some interesting empirical issues that have never even been raised, interesting questions that have never been raised before, primarily because of the first point. So at what point and how do children come to conceptualize numbers as actually infinite, given that they only conceive of them as potentially infinite if they're called Aristotelians, and as something other than the denotations of count words, namely cardinalities? I just gave you all that linguistic evidence that suggests cardinalities are not numbers. That's our judgments, or at least my judgments, and many other adult humans' judgment, or adult English speakers' judgments. My hypothesis at some point we had to make that transition. How does it happen and why? So those are two interesting questions I don't think anyone's ever raised before. And that's it. Thanks.
Take a 2-minute break. You can refresh yourself, get coffee, get whatever food outside, and we'll have plenty of time for questions. Okay.
Got questions, Eric?
I'm willing to address them. And so far as I can.
That makes no sense.
Not too bad, not too bad. It was quiet. Sometimes quiet weekends are the best weekends. Yes, absolutely.
Let's go for an hour.
No,
I don't know how long I was never for
So I think the Q&A goes until about 1:30.
Oh, I got plenty of time.
Yeah, I think it's an hour. The normal rule is that if people are still talking at 1:30, just go to cut off.
Oh, right, okay.
Yeah, I check it.
That's it.
So that's what
I was not tracking
Susan's
time.
thinking about.
They all felt like,
No.
Semantics
That was
is-
perfect.
oh, good, okay.
Exactly the way. No, that's the way it normally goes. I think perfection is the observation.
The important point is there's plenty of time.